programming. I'm going to walk you through the syntax and the basics of the Clojure language. And then we're going to go to those paradigms that are more specific to functional programming. But without knowing Clojure and not having seen the language before, it might be a little bit confusing. And the main thing is Clojure is a Lisp derivative. So Lisp, this is the thing with a parenthesis around it. So lots of parentheses. And if people are making fun of parentheses, but I don't see them anymore. And it's less code to type. If you write Clojure, and I've done Java, it's less code to type. And it's really just once you get used to that. So we have, in this language, we have the Scala values, the simple values, like numbers, and decimals, and so on, strings. Here's a single character that you can also have. And one thing that is special here are keywords. So you have the colon and a name. It's a keyword that's treated a little bit specially. It's much more performant. And it can be namespace. Think of it as a string with a namespace. And a namespace just provides collisions where somebody else uses the word foo in my thing. So you can say, okay, this is my namespace, and I'm the one who defines the word foo in that namespace. A short thing for the local namespace is the double colon. So things like UUIDs and instance in time, like date thing, are just done with a so-called reader and the reader macro. So you have this hash UUID and then a string, which then turns into, in the background, an object of a specific type. True, false, nil. Nil is the null value, basically. And you can start to type things here in the website if you want to try that out. So you can actually try some expression yourself. So if you have that, once you type it in here, the evaluated thing will appear down here. And Clojure is especially suited for those things because it's a so-called REPL language, which means read, evaluate, print, loop. So you take whatever you type in here, it reads it in, it evaluates it to the final value, prints it, and does the same thing again. So this is really a good way of learning it. So you can change something, and you see that it actually takes a string that is not complete, a complete date, and turns it into a full date here. And you can do that with all the other things above as well. So if you, for example, type colon foo here, you see that, sorry, I need to scroll it up for you. You can see that, okay, I typed the double colon, but what that really means, what it turns into is a Clojure script or Clojure .user namespace / keyword. So, okay, we'll win. We have lists, and lists are actually the only syntax that Clojure has. There's no other syntax than lists in general. Everything else is basically sugar to it. And a list, you can, you see here, this is already a function call. You turn that here into this list, and this is the parenthesis with different things in it. Arbitrary values can be complex. If you want to have a list directly, there's an apostrophe here in front of it, and it turns it into the same list. A list is a special construct because it is interpreted as a function call if you don't protect it with this apostrophe in front of it. So Clojure tries to take the first thing and treats it as a function. Now, if we take that apostrophe away here, it's an error because what does it say? Okay, here, 1 is not a function. I can call 1. I can't call 1. 1 is not a function. So in this case, it tries to interpret the first thing as a function call. Okay, so lists are here. We can add something to a list, and if we do that with a function called conj, so here the parenthesis, conj is a function call which takes this list here, which is 1, 2, foo bar, and adds a new value to it. And it puts it, paradoxically, it doesn't put it on the end, it puts it in the front. And that has to do with the way lists are treated in Clojure, which is as a linked list. So you only have a pointer to the first element, which then points to the next element, which then points to the next element. And when you want to add something, going to the end is very costly. You have to go through all the pointers until you add something. So lists, you just add something in front, point to the first. That's it. It's confusing, but logic and very performant. That's the most important thing. If you need something like, give me the 5th element, you can use vectors. Vector, like as a word here, or that's the most common way to define a vector. It just evaluates to itself. If you conjoin something, put something in that collection, you're going to add it to the end. And that's index. So 0, 1, 2, 3, 4 as index. So you can say, get me this element out of the index. And please ask questions if they come up, right? So don't be shy and try to, you can also play around with that while I'm talking. So here, maps are for more complex things, like what you think of objects in other languages. A map is basically a general tool to have some kind of data structure, like people, addresses, and so on. So first name Jochen, last name Rau, and that turns into a map. It's printed quite similarly. You don't have to have a comma here. It's just for readability. You can leave that out. There's no special thing. Everything that is not necessary, Clojure takes out of the syntax. That's very nice. And you can essentially take everything as a key value here, a string or anything you can think, a number, whatever you can come up with. So it's not bound to keywords. Usually, we take keywords. And if you want to put something on the map, you can join. You can conjoin something, for example. There are other ways to do it, but you can have a new value, conjoin it, and here you see it's added to the map. And not by order, it's an unordered map in this case. Yeah. And here you see an example of a deeply nested data structure with birth date and locations and addresses, 2 different addresses. And you see here, locations has a vector of addresses. So here's another map, but it's a collection of maps. It's a vector of maps, 2 different addresses. Okay. So, and one has a status of being current, which is actually true, right? So if that is evaluated, you get basically the same thing back. It doesn't look different here. Don't be confused. But this is evaluated, which you can see in the date, which is a full date here, for example.
What's that? What's the double colon here?
So the double colon means that I just wanted to. I could use a single colon, but I use a double colon just because if I hand around this map to other libraries and so on, and they have the same, they also have a status, and they call it current as well, but think of that as something different. Then we collide. You don't know what current it is. The double colon puts it into my local namespace. It's coming from me. It's its namespace. If they add current also with double colon, they have their own namespace, and it doesn't collide, right? So you can have names like current from different libraries. That's the okay.
When you're adding it, I think the map that looks like you do it, the new value is centered in your vector. Why is that?
Yeah, it's you could use a vector. You could also use a map. So what happens in the background is conj takes the argument and turns it into a sequence of any. So it's a sequence type. If it's a vector, it will be a sequence and then it will be added. If it's a map, it will be a sequence and then it will be added. So it doesn't matter what you take. It needs to be a sequence of 2 things. Okay? So I could use the map as well. What I can't do is let me see. You can also say I want to add bar, and that works as well. And as you can see, we can have multiple things here, but it's not ordered. See, this is kind of flipped around. So, did that answer your question? The usual way of doing that, by the way, is not conj, it's assoc. And so you would do that without the map. So it's the same thing basically. You associate a value into a map. That's the usual way of doing it. But I wanted to stick with conj. Conjoin is a very common thing. Okay. Oh, I will come to that later. I just want to go through the data structures and then go into how we can go into that a little bit, or fetch things out of the map or a deeply nested data structure. So here a set, from other languages you know that, it's a hash set is a unique, it's an unordered distinct elements. There's also an ordered set. And so if you look at that here, what happens if we, let's add another foo here. Sorry, here. So it will not allow me to have two things of the same thing. Set literal contains duplicate key foo. Key sounds weird. It's not a real map, but it's but there is the word foo twice in here. So I'm gonna take that out. And here, foo bar bots, I can conjoin a value, a new value here, like boom on it, and as a result, it will be in the set. What happens now if I turn that into bots? Anybody?
It's a duplicate. It's a different.
So right, it will not let it in because it would be a duplicate. So it will still have just one bots, but it doesn't lead to an error. It doesn't lead to an exception. So you can do that. It's kind of, oh yeah, I had that. I just already. Thank you, but no. So here, there's also a sorted set if you want to have sorted values, but that's different from you come up with a sorting, but that's not sorting that is preserved. It sorts it by key. So in this case, strings by natural sorting, VAR for VAZ and foo. So it's kind of, it sorts it for you, puts it in a specific place. So another thing are vars, and here, if you want to have a,
I guess that's about sorting. What does it use in terms of, for multi-byte characters? Where would they get sorted?
Multi-byte characters. Everything that Clojure does, and this is good at this point that you asked that, everything, Clojure is based or compiles down to JVM bytecode, Java bytecode. And that is, everything will be sorted as Java would sort it. It will treat, if you use a more recent version, it will treat UTF-8 or multi-byte characters in the right way. It will sort it like Java sorts it. But as you can see here, it also compiles down to JavaScript. So I can, if you have a Clojure code, you can compile it down to either a Java and which runs on the JVM, or you can compile almost the same code. So there's this kind of there's Clojure script and Clojure, but they overlap quite a bit. You can compile it down to JavaScript. So you write a lot of code. About 60% of my code that I write usually for multi-purpose, not only web apps but also data analytics is common code between the browser and the server, basically. So you can write it for both platforms. And that might be different if how multi-byte code is sorted on the JavaScript platform. So if you compile it down here, it might be different. It's just how the underlying thing works. So here, important concept are vars. So if you want to define something, it's like a variable, but it isn't. So a var, you define my name, Jochen, and you can refer to it later. Sounds like a variable, but in fact, you can never change. Once you define it, you can never change this variable again. So it's just there, and you can see that if we create a local context, like we have now, my name is bound to Jochen. Let construct, let my name be Sean, and I print my name within this let body, and then I output my name, then it prints Sean here within, but it outputs Jochen. It still has the old value, so you can never change it. That's the immutability, right? And if you if you go down here, if you finally define my name as Sean, then you will get Sean back. And oh, isn't that mutable again? So didn't I just say that it's not mutable, and now I changed it to Sean? It is, but remember, all the code that you write now, this is basically executed or read as one big thing. And the final thing that you define is the thing that is immutable, basically. You can't change that a var on runtime again. Yeah, this is not really runtime. Hi. Okay, let's go on to functions, because we need to dive a little bit deeper here. And it might take a little bit to load. And then it evaluates, so you can play around with it again. So what I said before was, okay, here, apostrophe, parenthesis. The apostrophe in front of the parenthesis keeps the, prevents the list from being evaluated as a function call. It just outputs the same thing. So that's it. If I don't have that, it will evaluate the first element of the list as a function call, and it hands all the other elements, the rest of the elements, into the function, which then, it's quite obvious what that does, adds it up. So instead of an infix notation, which is quite common in other languages, you have a prefix notation which takes all the arguments, can be arbitrary arguments, can be a fixed set of arguments, and evaluates it. So you can live change that. So it just takes that and changes that. Right. So okay, this is basically all you need to know to understand the syntax and the function calls from Clojure. That's it. If you want to reuse functions, a function is defined as, so if I want to write my own plus function, add up function, then I can do that with a so-called anonymous function, which is just a function definition, which is here fn. It's basically, I want to create a function. And then comes a vector of arguments. In this case, a function which takes a number. And what it does is, the body of the function here is basically evaluated with that number, and it adds 3 to that number. Right? So, and what you can see here, because we are on the JavaScript platform, it actually evaluates down or returns an anonymous function which is implemented in JavaScript. So it compiles down to JavaScript. Everything that you see here, you can write in Clojure, but it compiles down to JavaScript. So let's see how we can use that. We take that anonymous function, which takes a number and adds 3, and we put it in the first place in the list and hand in an argument, a number. So what's going to happen now, it first evaluates it to the function, and then hands it the argument. What the result is, of course, quite obvious, 8, because we call the function on the number 5. So we basically have created an adder at 3, and we can bind that with def to a name, because it's sometimes really annoying to not know what the function does. Give it a name and can refer to it to var. Okay, so we have now the same function that we had before, anonymous. We bound it to a var and call it add 3 to 5. So okay, same result, 8. So now it's much more, it's like the plus now. It's very easy to understand for your reader, and you can provide now a set of functions and create an API already. So okay, we get that. So that's a shorter version of that. Instead of def add 3 and hand in the anonymous function, we can also say def n, which combines the two things here, and I can get rid of one of the parentheses, which is nice. We have enough of them, right? Okay, we defined that, and we can now we can have nested evaluation. So we first evaluate a number and then call a function on that.
It definitely just makes it no longer anonymous. Is that so? Before you were giving an anonymous function a handle, but now you're actually defining a function that's not anonymous.
So the point where we come from anonymous function to giving it a name is already here. As we bind a function to the add3, everywhere where I refer to add3 is now this function, right? And that's the place where we go from anonymous to already giving it a name. This is just sugar, a helper, basically, so I don't have to def fn all the time. Because that's a very common pattern. You define a function, def, fn, it's just defen. Yeah. Defen, and you can basically just get rid of that and a parenthesis. Okay, so so here's a thing with when I have an add3 function, that's kind of a very specific thing, right? Add3, I want to have an adder, a machine that creates me functions like add4, add5, add6 on the fly. So here I define another function which takes an addon and gives me back an anonymous function. That's a return value. That's a point where it you really need to look at that closely, because that's a common concept. You return a function as a result of a function call. And then basically it returns an anonymous function. Instead of having 3 hard-coded here, we provide that as an argument. So I want to have an add10 function. And instead of writing add10 function, I just take that more general adder here, adder10, and that's going to turn into that function that adds 10 to it. Okay, that's the step to functional programming now. Does that feel like a cliff that you or is it just okay? So, and then of course you can, once you have that kind of higher level function that produces functions, you can do an adder10 and give it a name. You can then use it. So you can indefinitely use this, but you can also give it a name. And so you see we're peeling here the onions and the onion a little bit, and it's but once you're in this thinking of I can return a function or I can hand in a function as an argument, then it's really functional programming. Then you're on it, and it takes some time. It takes some time. So here the other way around. Instead of returning a function, what if we have we want to apply the add3 twice? So add 3 to 5 and add 3 to whatever comes out of that, right? Which is 11. So if we want to implement that as doing things twice with some function that I get, I don't even know what that is. It doesn't have to be an adder. It just can be something that I want to do twice. I define a function that takes a fun argument, a function as argument, and a number. Here we are a little bit specific because we only allow numbers as arguments. But, so we take that and do fun with a number. That's great fun. So for all purposes, we just did what we did before. Instead of writing it down at 3, we making it higher level and say whatever you give me as a function, I apply it twice. Okay. So and if you do that twice, you hand in a function at 3, and you get and you give it an argument. Then you apply this function twice and get 11. Same thing as before. So let me try what happens. We defined. So I can also take add 10, of course. I can change the function. Now I'm really flexible. I can hand in the add 10 that I just created up there and apply it twice, and you got it. So 25. So it's kind of the nice thing that this is. We're in the thing of higher level functions now. And this is quite powerful if we apply a function to a collection. So if you want to consume data, basically, you have a collection, a vector of 3 numbers, and you add 3, and you map that on each of the elements. What you get is, you get back a sequence that looks like a list, but in the background it's a sequence of numbers or of values, which are add 3 to 1, add 3 to 2, add 3 to 3, and that's it. So map is basically the step where you apply to a large collection. One of the powerful things. The next thing is, you might have heard of Mapreduce or so, might be familiar with that. Reduce takes a function, and the first and second element of a sequence or a collection, and applies that to the first elements. Then takes this value and applies the function again to what I have and the next element and the next element. So it consumes bit by bit the whole sequence of numbers, right? So when I type 4 here, that would be easy because I could just use the plus. It's get more complicated if you have more complicated functions than plus. So you can basically consume any kind of collection, map over it, and reduce it. And if you look at that, we map add 3 over it, and then without doing anything else, we just take that value of 4, 5, and 6, and then reduce it by adding it up. It's 15. So that's Hadoop, basically, in one line. You don't have to spin up servers, and it's kind of messy. You just write one line in code in Clojure, and you're done, essentially. So spare you that. We don't need that really at the moment. You can play around with that later. What we need, though, is filter. For example, you can say filter and give it a function, which then returns a truish or falsish value. And for all the truish values, it puts it in a sequence, the result, and hands back the sequence. So give me all the even numbers. Or do we have an odd function? Right, we have an odd function. Or we can, any function you can also complement and get back the even thing. So which is probably how they do it in the background. So okay, now back to the question how we can, is functions are okay? Let's move on to data structures. We have the same thing here, getting access to a deeply nested data structure. Let me check on the time. Okay, so here we have basically the same thing as before, this kind of nested thing, birth date and so on, and we assign it to Joe, in this, which is my Starbucks name because Jochen, nobody can really understand Jochen behind the counter. So here, and you see here I defined it, and it's now in my namespace Joe, and now I can say get the first name out of Joe. And that's Jochen, right? And you can shoe size, for example. You can also by saying get, you can it's a very common thing in language, so that should be obvious. You can also get things out of it, which is little bit painful. And keep in mind, Clojure evaluates from the inner to the outside. So first you get the locations. Locations is a vector of things, and a vector is indexed by 0 index number, so there's 0-based sequence. So when we get out of the locations, get 0 location means the first location that is in this vector. And we get out of the location the city. So Amherst. So this is, if you go back to the data structure, basically the value that sits here. So out of the first location, we get Amherst. There's a faster way of doing that, of course, that's get in Joe, locations 0 city. So you hand in a vector of basically your graph, you're going into the graph. And it's the same thing. So instead of get in saves your life. Here comes something weird. Keywords are functions. That's a thing. Instead of a string is not a function, but a keyword is a function. That's why people use keywords in maths. Keyword is a function call, and it's basically doing the get thing, but shorter. And that is especially neat if you have if you get the locations out of it and map the city over that. So you get the locations and get of every location the city out of it. And what do we have here? We can, yeah. So here we are. No, so take the zip code out of it, for example, right? So that's helpful. Let me see if we can do anything else here. No, let's go here. Let's see what that does here. This is a longer, more elaborate line of things. Can somebody explain what it does here?
Taking the location when the status has to match current.
Right. So here, that's a filter. It filters the locations. Get the locations, filters the locations, and only the current. And here, double colon again. So I'm sure that it's my current thing that I want to have. So not somebody else's current. And it gets the first one of that, and you just have one current address. So
If there was no current address, would you just get another?
let's take the current out of the thing here and see what that should. Let's see if that evaluates it. No, it would get nil. Yeah, it would. Yeah. So here again, in short, conj, if you have different elements, if you want to add something to it, a vector adds it to the end. Yeah, that's the result. That a vector adds it to the end. A list adds it to the front. Set just puts it in without order, and doesn't put the double in it. So that's what we had before. So let's go down and one more thing, and then we're gonna go one step further into other concepts. So when we want to update something in the data structure, we need to reach in and change something. In the function programming language, that you hand in a function that changes the value. So what you do here, update in Joe at location, at the 0 location, at the first location, dissociate, take out the status, which does basically the thing that you wanted. And so if we do that, let's take that out here, you will see that there's no status here anymore. So I just took it out, the current status. And keep in mind, it's immutable. So if I type in Joe, instead of updating in Joe, that it's always just the last thing that is returned, the last thing in the line that is returned. Joe is still the same. So I did not actually change Joe at what I did at the very top. That still has current here. I can change it at the top. That's still the case. But if I update it, and I can say def new Joe, and I will have that value. So I have to really give it another name, a different name, or no name at all. Usually you don't give it names. Okay, let's go to laziness, and that's a very important concept. So range, the function range just gives you numbers from 0 to 10 here in this case, or to 100. You can expand that, or if you just hand in one argument, this number, it starts at 0. So it's quite simple. But this function enables you also to not hand in any number, and what it does is it keeps on going. It's basically, and if I take that out here, my browser is not really happy about that decision. So it's gonna, we need to get it back here. Okay. Actually, that was a little bit, it will stop because the thing that I use in the browser will stop to continue because it detects this is not gonna work out well. Okay, so, but what does it do? If I have range here, and I just told you that Clojure goes from the inside to the outside, it would evaluate the range. It would give this infinite number, a list of numbers, and it would crash. But what Clojure does is it's lazy. It waits until it really needs to evaluate something. It's really, if I say take 10 out of this range, it knows that it doesn't have to evaluate up to 1 million or infinite, and to take the first 10, it stops at that. So take 10 is perfectly fine. My browser's happy here, right? So I can measure the time it takes to end is a function that takes out of a sequence the element or at the position that I give it. So here, range, indefinite numbers, list of numbers. I take the whatever billions, millions here, and I measure the time, how long it takes, and it's very fast. So it's a very fast access to that range when I give it, when I don't have to evaluate every single value in between. So it's fast, and I get the number. So what happens here when I take that out? What does it do here? Maybe somebody can see how my browser feels. So map means that I whatever function I give it, it applies to each element. It's not creating a hash map like we had before. It's applying this inc is increase, means increasing by 1, a number by 1. So what will happen if I take that out? Which is, by the way, commenting it out. So hash comes out. What will happen?
Million numbers and add 1.
Uh-huh.
Return a list of the first million numbers.
Increase by 1. So it will
From 2 to 1 million.
right. So it will, or we start at 0. So it will 1,
0 to 1.
2, 3, 4, and it will return. Okay, let's see. Yeah. Okay. So okay, what it did basically, yeah. We don't see it in between, right? We don't see it, but it increases every value. It doesn't know what to do with it. It has to increase it first, and then we can take out one thing. And it's much slower because it's not lazy. It's still lazy. It doesn't do the trillions of trillions, but it goes so far it can go and has to do the work. So the work, you see, is quite a bit. So okay, next. What happens here? What happens if is my browser still? Yeah.
So would that, I'm not certain what the behavior would be exactly, but would that go across the entire, like that's no ending, it's just saying you should print the number when it equals 1?
Oh, so yeah, needs a little bit of explanation, right? The print line is a thing that is a so-called side effect. So usually, if you have Clojure, you don't have side effects. You just create a value that comes out of the function. But sometimes, like going to the databases, so you want to have a side effect, which Clojure allows. And printing something to the console or something is a side effect of what you do. So there will be a side effect of printing a number as we go along here, as we filter. So the filter has an anonymous function. Here, you know that here, what that means. It does this kind of thing. But the filter takes every single number, 1, 2, 3, and so on, and returns a truish or falsish thing. So and it filters those things out that have this where the number is 20. So okay, what? Let's see. Nope, it's just fine. Boom. Why is it so? Let's make an observation here. 1, 2, 3, 4, 5. It starts with 1, which was expected because we increased the whole thing. It ends in 2020. Why does it end in 2020 and not in? Yeah.
Is it printing number 20 in the end because 20 equals 20? It stops evaluating and returns first?
Right. Right. Here. Yeah. Prints it. Oops. Returns it. It's the first. the thing with the first is, once I have it, once I have one of which I want to filter, I'm done. I just want to have it first. While this, if I look at this only, I would filter it and look for 20s. But I only need the first one. So let's.
If you took the first out, it would keep going because it could be other
Oh. I need to. No. See. Okay. Yeah. That was the talk. It's frozen. It's kind of okay. Yeah. So it's basically done. So now I have to kill the page and reload it. Or it will kill itself. So. Because it's not, it's just, you can't destroy the page by taking out. You can try it for yourself. So yes, once there's the first is out, it doesn't know if there are more 20s. So it needs to search and search and search and search and search. And one observation is it doesn't even print. It doesn't even do the printing, right? It could basically go on with the printing. Not even that. It doesn't go, because it's still, Clojure needs to figure out what to do. And before it actually prints something, it just keeps on trying to get all those values together. So no. So, but you see, it's powerful lazy evaluation, but it's also one needs to understand it to use it, and that's sometimes quite complicated.
So you're saying it's getting stuff and figuring things out without actually doing the work?
Oh, it does the work. No, the browser is busy going through that list, but it doesn't invoke the print line as a side effect at all. The browser actually it invokes it, but the browser is busy going through that. It doesn't show. It doesn't update because it hangs at the moment where it's. So this is kind of how it's underneath. I'm not completely sure because that also depends on the JavaScript and virtual machine. But it's kind of, it keeps on going through that list and never stops, and it never gets to the place where it can actually does the updating of the UI basically. I'm sure it issues the command to print, but the UI doesn't react to it. Okay, we have 10 more minutes left, so that's perfect when you're already a little bit tired to go to recursion, because that's it's a fun thing to do. So factorial of 8 in math, it's basically just multiplying all the numbers up to the number 8, which gives us 40,320. So if we wanna basically make that flexible as a function, we could, and this is the common way to do it, we could say, okay, let's make it recursive in that we define a function defin factorial that takes a number, which is then should be 8 or whatever I want to have the factorial of, and something that is an accumulator. And we'll look at that later. Why we need that? That's the question. So if the number n is 0, return the accumulator. Return what you currently have, or call the function factorial from inside basically, with the number that I gave it in the first place decreased, and the number that I currently have multiplied with the accumulator. Ooh, okay. What does it do? So if you look at that factorial, I hand in 8, I have an accumulator, which is basically the start element to have 8 times 1, right? Once I'm here, I'm going in, I have 8 here, it's not 0, so I go to that. I call factorial, I decrease n, which is then 7, I call it with 7, and 8 times 1. So now I call it with 7 and 8, right? So now I call it. Is it 0? 7. So I call it with 6, and now I have 8 times 7 here, right? And so it keeps on going, and I hand in the accumulator and the decreased number, and until I hit 0, and I return the accumulator. So that's a crazy concept of recursion that usually you get not in touch with in a functional, in an object-oriented programming language, where it's rare that you use a method that calls itself. Even going to another method which then calls back and so on. So because usually one is afraid of, oh, I'm gonna get stuck in infinite loops or something, right? So it's kind of this, oh, I want to avoid it. That's actually the only way you can loop in Clojure. There are some constructs that makes it a little bit easier, but recursive calls are the only way to loop. And that's for a reason. That's makes it incredibly powerful to not have to hold on to some state. You hold on here to some state. You can basically it evaluates the inner and the outer and so on. Sorry, this has state, but there are constructs down there that avoid having state, so you're much more fun. Yeah.
So are there like many consequences, or is it taking a lot of
Recursion is actually one of the things that creates less overhead as you would program something like that as a loop, basically. Because the loop, later on we don't hold on to that thing, but as a loop, in a loop you have to hold on to some state. That creates a memory problem. In Clojure, if you do it, if you recurse from the right position, the so-called tail position, you don't have to retain the value that you calculate. You just create it and hand it in and be done with the auto call. So or the inner call. So you're done with it. You don't have to hold on to that until you evaluated everything.
Is that why you use the accumulator? You're not holding it in memory because you put it in the calculator.
So let's take a no, the accumulator. The accumulator is actually necessary to here if we would, let's go to that construct. The accumulator is actually the state that you hold. In this case, it has a memory memory penalty. You hold on to it. But here is the Clojure construct that is actually used, and there you don't have an accumulator from the outside. You don't give it from the outside. So there's a loop construct that you have a counter, which is basically the 8, 7, 6, and so on. And you have the same question here. Like, is the counter 0? Then return the accumulator. And inside this loop, you define the accumulator. So you don't actually, from the outside, hold on to that. And then here is a special construct. It's called recurse, and the same thing that we had before, basically. So in having the loop recur construct, you don't hold on to this accumulator from the outside. And then it's extremely memory efficient. You're just doing whatever you do inside this loop body. Right.
This is another set of commands to achieve the same thing as what we did.
Right. It's the same thing, but it's the Clojure way of doing it without retaining the state of the thing.
So is it actually calling the function again, or is it
Yes. Yeah.
outputting inside the loop?
It's not calling the function again. It's calling the loop. So that's why we don't need the. It's basically within. This construct, it's within this factorial that we loop. So that's what you use, and that's quite powerful. There are a couple of ways of doing it easier, but that's basically it.
And so the idea of Clojure is, because they're immutable objects, is that it just every time it creates a new object, it destroys the old object.
Right,
Just
right.
ending up with the most current object.
Correct.
Whereas if you were doing recursion in JavaScript, which you can do by calling kind of an intermediate function that calls the original one, if you write out the console, you'll see that as deep as it goes, it has to return control all the way back up the exit.
Right, which makes it a pain in JavaScript, memory intensive to recurse and quite error prone. In Clojure, you don't have that. If I don't recurse from the tail position, and if I have a state, for example, and that's the last thing I can do, but I want to be respectful, and I say here increase. It doesn't, because I cannot retain it. I have to increase it once I need to retain the value that comes out of that, because I have to increase it after I gain. So that prevents this kind of letting go of the value. You need to have it still, and it rightfully does so. It says can't recur here at line 6. So I need to be at the last thing that I do is recurse. Then it works. And Clojure makes that sure to do that. Okay, so those were the things. State is some special things. That was just an add-on. The next hour I would spend on how to develop a web application with Clojure from scratch, but I don't have that. Any questions outside? Any questions? We need to leave the room. They are standing outside. Meet me outside because I want to be respectful for the next speaker, and they need the room. Thank you very much. All right.
There we go.